Ah, here's the moment you've been waiting for all chapter. As a matter of fact, I've been teasing you about it pretty much from the beginning of the chapter. We're now going to talk about the shape of molecules and its effect on the polarity of a molecule. The shape a molecule is going to take can be predicted using what's known as VSEPR theory, valence shell electron pair repulsion theory, which, just as an offhand remark, I've always thought VSEPR would make a hell of a name for a secret organization in a James Bond movie or in a spy movie or even an Austin Powers movie, right? VSEPR. It sounds like a secret evil organization if you ask me. All right. VSEPR, a valence shell electron pair repulsion theory. What it says is it says that the electron pairs around a central atom want to get as far away from each other as possible. Why is that? Well, they all have negative charges, and like charges repulse each other. Another way of thinking about it is the electron pairs around a central atom are like two kids in the back seat, right? They want to get as far away from each other as possible and are always playing the "will you stop touching me" game. So that's all VSEPR is really saying. But because these electron pairs want to get as far away from each other as possible in three-dimensional shape, in three-dimensional space, their desire to get away from each other is going to dictate the shapes of molecules. Here are the shapes to predicting molecular geometry. Even though your book gives you this three-step process, it really boils down to two steps. One, you're going to write the Lewis structure or the electron dot structure that we talked about earlier. Next, you're going to count the number of bonded pairs of electrons around your central atom and the number of unbonded pairs around your central atom. This ratio will dictate the shape of the molecule. Let's take a look.
For the purposes of this class, there are three base shapes in which electron pairs can arrange themselves, and all other shapes are derived from these three fundamental shapes. Whenever you have two electron pairs, the farthest two things can get away from each other in shape is 180 degrees. Whenever you have three total pairs of electrons, the farthest they can get away from each other in space is 120. And on a plane, we're talking three-dimensional here, right? Tetrahedral is the farthest away four electron pairs can get away from each other in space. You'll notice that the drawings in your text are a little bit confusing. If you study those drawings, you'll notice that we're talking three electron pairs, but you have four balls drawn. That's because the ball without dots in it represents your central atom. And what we're talking about is how the electrons arrange themselves around that central atom. Alright, let's talk about the modifications that you can make to these fundamental structures to get your other structures. Okay. This page shows you two tables that are extremely important in working VSEPR. If you were taking this class in the traditional format, I would tell you had to memorize the contents of these charts. However, you have the benefit of taking this class online. So if you're preparing a series of crib sheets for your online exam and quizzes, or even for just doing your homework, this is a sheet I would recommend printing out. This provides you a very easy method of determining the shape of any compound. Let's look at the headings to our columns. First, you'll notice the first column has the heading General Formula. AX squared, for example. A is your central atom, X is your non-central atom. The next column is the total number of bonded atoms. Your third column is the number of unshared electron pairs. Those are the two important numbers. Those are the two numbers that are going to determine your shape. Whenever you have the sum of those two columns equal to 2, your shape is going to be linear. Whenever the sum of the number of bonded atoms plus the number of unshared electron pairs is 3, your electrons are going to arrange themselves in a trigonal planar. However, when only 2 of the 3 electron pairs are involved in covalent bonding, your shape will be bent. And you're saying, wait a second, I thought you said trigonal planar. Take a look at the picture there of the bent molecule. You have 2 bonded pairs of electrons and 1 unbonded pair. When we talk about molecular shape, we're only talking about the shape made by your bonded electron pairs. However, those bonded electron pairs still feel the repulsion of the unbonded pair. Therefore, rather than being linear, they're bent because they have to move away from that unbonded pair, right? This pattern becomes even more clear. This concept of repulsion, or the effects of your unbonded pairs, becomes even more clear when you look at molecules where your total number of electron pairs around your central atom is 4. When you have 4 total pairs of electrons around your central atom, those electrons are going to arrange themselves in a tetrahedral. When all 4 are bonded, your molecular shape is also a tetrahedral. When 3 of the pairs are bonded and 1 of the pairs is unbonded, the electrons still arrange themselves in a tetrahedral, but you're only interested in describing the shape made by your bonded pairs. So you have what looks like a pyramid, and it's called trigonal pyramidal, right? Instead of trigonal planar. Why? Because you have that lone pair pressing down on your bonded pairs, right? Instead of being flat in a plane, they're being pressed down. Finally, if you have 4 total pairs of electrons around your central atom, 2 of them are bonded and 2 are unbonded, your electrons are going to arrange themselves in a tetrahedral, but you're only interested in looking at the bonded pairs, and they're going to make a bent shape. Memorize this chart, learn it, love it, live it. This is another sheet that you're going to want to print out. It contains the rules for determining VSEPR. Basically, all this sheet boils down to is, A, you're going to draw the Lewis formula for your molecule, just like you have always done. And once you've drawn the Lewis molecule, you're going to count the number of bonded pairs of electrons around your central atom and the number of unbonded pairs around your central atom, and use the chart from the previous slide.
Alright. Here is the structure of beryllium chloride. Now, this is an exception to so many rules, it's not even funny, and I hate the fact the book is using this as an example. But without having to write the Lewis structure on your own, here it is given to you. Note, beryllium's an exception to the octet rule. Beryllium's your central atom. VSEPR says that the electron pairs around your central atom want to get as far away from each other as possible. What's the farthest 2 things can get away from each other in 3-dimensional space? 180 degrees, or in a line. Because those 2 electron pairs around your central atom want to get as far away from each other as possible, they'll make a molecule that forms a line. And we would say that the shape of the molecule is linear. Something to note important as we discuss VSEPR is that double bonds and triple bonds really function as if they were a single bond. The reason for this has to do with the way they exist. You can think of single bonds as being hot dogs that connect the 2 atoms. Double bonds, rather than trying to get really far away from that single bond, double bonds actually lie around the single bond like a hot dog bun. And when you have a triple bond, that triple bond encompasses the 2 sides that aren't covered by your double bond, kind of making it a hot dog shape. What I'm trying to say here, rather confusingly, is double bonds lie in the exact same plane as the single bond. Therefore, when you have a double bond or a single bond, when you have a double bond or a triple bond, you're going to count them in terms of VSEPR as if you had one single bond. For example, carbon dioxide. You see the Lewis structure of carbon dioxide right there. Rather than saying that you have 4 electron pairs around your central carbon, you say you only have 2 electron pairs. You count those double bonds as single bonds. And the farthest in three-dimensional space that 2 things can get apart is that 180 degrees again, or that linear shape. So that's just something to keep in mind. See, this is what I love about VSEPR. The fun just keeps building because we looked at central atoms with 2 things around them, and now we get to look at central atoms that have 3 things around them. We have boron trifluoride here, and what you'll notice is in your Lewis structure, you have 3 pairs of electrons around your central atom, boron. Remember, when we talk about VSEPR, we're only interested in electrons around our central atoms. The electrons around our non-central atom are irrelevant. They don't play a role in your molecular shape. Just the electrons around your central atom. Well, the farthest that 3 things can get apart in space is 120 degrees. What this looks like is it looks like a flat structure, as in all 3 of your outlying atoms are all in the same plane, and they're separated into what looks like a triangle shape with 120 degrees between them. Because we're flat, we refer to the structure as planar, and because it looks like a triangle, we call it trigonal. So our shape is trigonal planar, or trigonal planar. You say potato, I say potato. One thing, if you're having trouble conceptualizing what we're talking about, it will help to get a cheap bag of balloons from Walmart. If you get the balloons and blow up one balloon for each pair of electrons around the central atom and tie the mouthpieces of those balloons together, you'll automatically get the shapes we're talking about here. For example, if you want to see what a trigonal planar would look like in terms of 3 dimension, let's get 3 balloons and tie their mouthpieces together. Each balloon will be one of those pairs of electrons around your boron, and where the mouthpieces come together, you'll have boron. And you'll see how those 3 balloons want to get as far away from each other as possible, and the only way they can get as far away from each other as possible is to form a trigonal planar. And that balloon technique will work for any of these shapes we're talking about here. Up till now, all the electrons around the central atoms that we've looked at have been bonded. What happens when you have a lone pair of electrons? Let's take a look at sulfur dioxide. Your Lewis structure of sulfur dioxide is shown there. You have a double bond between sulfur and one of the oxygens, a single bond between sulfur and the other oxygen, and a lone pair of electrons on the sulfur as well. That means you have 3 things around that central atom, 3 pairs of electrons. The farthest those 3 things can get apart in space is a trigonal planar, right? Your electrons are going to arrange themselves in a trigonal planar just like we saw in the last slide. However, this time there's no atom at the end of that pair of electrons. And when we talk about molecular shape, we're only interested in the bonded pairs. Therefore, the shape formed by our molecule looks like a boomerang and is bent. We still see the effects of that unbonded pair of electrons repulsing the bonded pairs. If we looked at all the electrons, we'd see a trigonal planar. But when we talk about molecular shape, we cover up that unbonded pair and look just at the bonded pair, so it looks like it is bent. That lone pair is repulsing those 2 bonded pairs still. Alright, now we get to begin talking about carbon's favorite shape. Carbon loves to be the central atom, and it can always have a maximum of 4 electron pairs around it. The shape formed by 4 bonded pairs of electrons trying to get as far away from each other in space is referred to as a tetrahedral. And a tetrahedral kind of looks like a triangular shaped pyramid with your carbon atoms suspended in the center of that pyramid. Your bond angle there is 109.5. Tetrahedral. Now what we're going to do is we're going to change up and make several shapes out of that tetrahedral by having some of those pairs of electrons around our central atom be unbonded. When all 4 electron pairs around a central atom are bonded, it's a tetrahedral. Let's look what happens when one of those pairs is unbonded. Here you see the electron dot formula for ammonia. Notice that you have 4 electron pairs around your nitrogen. So those 4 electron pairs want to get as far away from each other as possible. The farthest that they can get away from each other in 3-dimensional space is to form a tetrahedral. So those 4 electron pairs are going to form a tetrahedral. But when it comes time to talk about molecular shape, we only look at the bonded pairs. So look at that second figure. You can see how your electrons arrange themselves in a tetrahedral. But when it comes time to talk about molecular shape, we look at only the bonded. And if you look at those bonded, they seem to be forming a triangular-based pyramid. So we refer to it as trigonal pyramidal. Do you understand the difference here? When we talk about molecular shape, we look only at the bonded electron pairs. However, we still see the effects of the unbonded pair. Alright, let's look at another tetrahedral-based molecular structure. Let's look at water. Look at the Lewis structure of water. If you look at the Lewis structure of water, you see once again you have 4 electron pairs around your oxygen. Whenever you have 4 electron pairs around something, those electron pairs are going to form a tetrahedral. However, this time, 2 of those electron pairs are unbonded and 2 are bonded. When you have this situation, you're going to get what's known as a bent molecule again. Why? Because you have that boomerang shape. You still see those 2 unbonded pairs repulsing your bonded pairs. Just like the earlier slides, this slide serves as kind of a great summary sheet or cheat sheet for you to study with, breaking down the ratio of bonded atoms to lone pairs atoms and the molecular shape that you're going to produce based on that ratio. And another great sheet to print out and study.
What is the shape of the nitrite ion? They're throwing you a little bit of a curveball. When you draw your Lewis structure for your nitrite ion, one thing that you're going to have to keep in mind and watch out for is because you have a negative charge there, that means you have 1 extra valence electron. Right? When you're counting up your building fund for nitrite, you have 5 valence electrons from your nitrogen, 6 from each from 2 oxygens for a total of 17, and then you have a negative charge, so you add 1 more, because that's the meaning of a negative charge, you have an extra electron, for a total of 18 valence electrons with which to build. Okay, you've drawn your Lewis structure, and as long as you're drawing the Lewis structure for an ion, let me point out what they did. Whenever you draw the Lewis structure for an ion, you have to place that Lewis structure in staple brackets and write the charge as a superscript out to the upper right-hand side. Now what you're going to want to do is to determine the shape of the molecule, look at your central atom, in this case your nitrogen. You have 1 unbonded pairs of electrons, and you have 2 atoms bonded to your central atom. So that means that the electrons are going to arrange themselves as a trigonal planar. But because you're only interested in describing how your atoms are arranged, the shape is going to be a bent shape. Let me comment at this time real quickly about why that bond angle is 118 as opposed to 120. The reason being is that a lone pair of electrons is more repulsive than a bonded pair, right? If you think back to when you were in high school and everybody had coupled up, there was always that one guy who'd never been on a date, but yet always insisted on sticking around on everybody else's, right? That lone pair, and man, was he ever whiny and repulsive, right? Therefore, your lone pair is going to repulse or press down on your bonded pair more than another bonded pair would. So your angles between your bonded pairs is going to be less than 120. And the standard way of estimating that is to take 2% off. So your 120 becomes 118.